here to talk to you today about thermodynamics. Thermodynamics is a branch of physics that deals with the work and energy of a system. More specifically, it deals with thermal energy, how it is converted and transferred, and how it affects matter. It began in the 19th century when scientists were trying to discover how steam engines work. First of all, we need to define the differences between temperature, heat, and thermal energy. Temperature is the measure of the average kinetic energy of molecules in a system. Thermal energy is the energy possessed by a system due to the movement of molecules. Heat is what's known as a process quantity, meaning one thing in itself does not have heat. For example, this hot coffee does not have heat in itself, but the heat is being transferred to the mug, which is then being transferred to my hand, which is why my hand feels hot. Heat is what's known as a process quantity, meaning one thing in itself does not have heat. Heat is the difference in temperature between two systems. For example, the coffee in this mug does not have heat, but heat is being transferred to the mug, which is then being transferred to my hand.
There are 3 laws of thermodynamics. Law 1 is the conservation of energy. Energy can only be transferred or changed from one form to another. Total change in energy is equal to the heat of a system plus work performed by the system. The second law of thermodynamics states that entropy of an isolated system always increases over time. Therefore, the entropy of the universe is constantly increasing. The third law states that entropy of a system approaches a constant as temperature decreases. Absolute zero is the lowest temperature that is theoretically possible, but it has never been reached. Now let's look at energy transfers. Energy is transferred between objects when a reaction occurs. The essential patterns of energy are as follows. Heat transfers from high temperatures to low temperatures, and energy transfers from molecules colliding into each other. When calculating the amount of energy involved in a reaction, we focus on the initial and final states of the reaction to find the change in enthalpy, entropy, and free energy. Enthalpy, entropy, and free energy change are all state functions, meaning they depend on the initial and final states of systems rather than the reaction pathway. Most of the time, substances are assumed to be in standard state conditions. This means that liquids are pure, solids are pure, gases are at a pressure of 1 atmosphere, solutions have a molarity of 1, temperature is almost always 25 degrees Celsius, and the energy of formation of an element in its normal state is 0.
The heat of formation, otherwise known as enthalpy, is the change in energy when 1 mole of a compound is formed from pure elements under standard state conditions. If the total change in enthalpy is negative, then the reaction is exothermic, and energy is released. This also means the products are more stable than the reactants. If the total change in enthalpy is positive, then the reaction is endothermic and energy was absorbed. In this type of reaction, the reactants are more stable than the products. Something else to remember is the change in enthalpy for any pure element, even diatomic molecules, is 0.
Bond energy is the energy required to break a bond. Breaking a bond is always endothermic. The change in enthalpy is equal to the sum of bond energies of broken bonds minus the sum of bond energies of formed bonds, with units in kilojoules per mole. Total enthalpy change can also be found by subtracting the sum of enthalpy change of the reactants from the sum of the enthalpy change of the products of the reaction. Hess's law can be used to find the total amount of energy released or absorbed in a reaction. Using the law, you can manipulate a reaction by flipping it and reversing the sign of its enthalpy value, multiplying or dividing the equation, and using several equations to sum up to one desired equation. The enthalpy values of the individual equations are then added together to find the total enthalpy of the desired overall reaction. When an ionic substance dissolves in water, heat is either released or absorbed. The breaking of bonds requires energy, but energy is released when the cation and anion form attractions with the water molecules. The substance dissolves in 3 steps. First, the solute bonds break apart. Then, the molecules separate. Finally, the solute molecules form new attractions to the water molecules. The energies of the second and third steps are called the hydration energy, which is always negative because energy is always being released in these steps. The sum of the energies of all 3 steps is the total enthalpy change of the solution.
The amount of energy that molecules have determine their state. Once they reach a certain threshold level of energy, the substance undergoes a phase change. Phase changes are always physical changes, which means they do not involve breaking bonds or creating new substances. The pressure exerted by molecules who have enough energy to break away from the solids and liquids into gas is called vapor pressure, and when the liquid or solid phase is at equilibrium with the gas phase, the pressure of the gas equals the total vapor pressure of the substance. Another thing to note is as temperature increases, vapor pressure increases because the molecules are increasing their kinetic energy and therefore are able to break away from the liquid and solid phase.
When vapor pressure equals atmospheric pressure, the liquid is considered boiling. The change in a substance from solid to liquid is called melting. Liquid to solid is freezing, liquid to gas is vaporization, gas to liquid is condensation, solid to gas is sublimation, and gas to solid is deposition. The energy needed to melt a solid is called the heat of fusion. Intermolecular forces are more strong and stable in the solid state than in the liquid state, so energy is released when a substance is frozen. The energy that is needed to melt the substance must overcome the forces holding together the solid to break the bonds. Specific heat capacity is defined as the amount of energy needed to raise the temperature of 1 gram of substance by 1 degree Celsius. Calorimetry is the measurement of heat changes during chemical reactions. Entropy is the measure of randomness within a closed system. Zero entropy is defined as zero solid at 0 Kelvin, which is absolute zero. Change in entropy in a chemical reaction equals the sum of entropy of the products minus the sum of entropy of the reactants. Gibbs free energy is a measure of whether or not a chemical reaction is thermodynamically favored, meaning the reaction can proceed without additional energy. Reactions that don't need outside energy are called spontaneous, and reactions that do require additional energy are called non-spontaneous. Non-spontaneous reactions are not thermodynamically favored. In the upcoming demonstration, you will see thermodynamics in action. Our team dipped cotton balls in a solution of water and isopropyl alcohol and then set them on fire. The combustion reaction causing the isopropyl alcohol to burn is spontaneous. The isopropyl alcohol also burns with a cool flame, so the fireballs can be held in the palm of your hand without burning your skin.
Hold tight. Wait till the party's over. Hold tight. We're in for nasty weather. There has got to be a way. Burning down the house.
Chemical reactions can create a flow of electrons. We can measure how much voltage there is between two half cells of a battery with the cell potential. If the voltage of a cell is positive, then the reaction is spontaneous, and vice versa. Thermodynamics is essential to understanding daily reactions, like why your tongue gets burned when you drink hot coffee, or why salt dissolves in water. Topics we learned about today, covering the scope of thermodynamics, include enthalpy, entropy, Gibbs free energy, bond energies, phase changes, calorimetry, and voltage. Thanks for listening!